Hello everyone. Today we'll study how to find volumes of solids. In general, finding the volume of a solid is not easy. But here, let's look at a simple case. Find the volume of a solid obtained by rotation. Let f of x be a positive continuous function on the interval from a to b. And let R be the region under the curve on the interval from a to b. Let me show you the picture first. Assume f of x is continuous on the interval from a to b. Here, make it simple. Assume that's the curve, y equal to f of x. And f of x is continuous on the interval from a to b. Assume that's a, that's b. R is the region under the curve on the interval from a to b. So that's region R. When R is rotated around the x-axis, the volume of the obtained solid can be found as the following. When R is rotated around the x-axis, we have a solid looks like this. When R is rotated around the x-axis, we have a solid looks like this. That's a solid. We will rotate R around the x-axis. And we try to find the volume of the obtained solid. We try to find the volume of this obtained solid. How can we find the volume of this solid? In order to find the volume of this solid, let me first of all cut the interval AB into n subintervals. I first of all cut the interval AB into n subintervals. And on each subinterval, I pick sample point. Use the sample point to approximate a rectangle. Then rotate the rectangle. I can apply a cylinder. On each interval, pick sample point. Use sample point to approximate a rectangle. Then rotate the rectangle. Its volume is a cylinder. On each subinterval, pick sample point. Use sample point approximate rectangle. Rotate the rectangle around the x-axis. It's a cylinder. Pick sample point on each subinterval. Then use the sample point to approximate rectangle. Rotate the rectangle, we have a cylinder. Do the same thing for each subinterval. And we can see that this volume is very, very close to the actual volume here. Now, how can we find the volume of this shape? How can we find the volume of this shape? We can see that here, each piece here is a cylinder. The volume of a cylinder is base area times the height. The volume of a cylinder is always the base area times height. Let's look at the nth subinterval here. Let's look at the I subinterval here. Assume that's xi minus 1, and this is I. This is Si. Assume that's an I subinterval. Let me draw an I subinterval here. let me draw the I subinterval here. That's the interval from A to B. We cut interval A, B into n subintervals. So that's x0, xn. Assume somewhere in the middle, that's x sub I minus 1. That's x sub I. We pick sample point here. That's f of si star. We pick sample point here. That's f of si star. Then use this sample point to approximate the rectangle. Notate a rectangle with a cylinder. That's one of the cylinder here. That's one of the cylinder here. Now try to find the volume for this cylinder. We know that the volume of a cylinder is base area times the height. And the base area here, the base is a circle. For this cylinder, the base is a circle. Area of a circle is pi r squared. Area of a circle is pi r squared. So we get pi times r. Here r is the height of the cylinder. R is the height of the rectangle. R is the height of the rectangle, which is f of si star. That's the radius. The radius is the height of the rectangle, which is f of si star. That's the base area, pi r squared, times the height. The height is the width of this rectangle. The height is the width of this rectangle. And the width of this rectangle is delta si star. That's delta si. That's the width of this rectangle. The width of this rectangle is delta si. That's the width of this rectangle, delta si. Then this is one of the piece. In order to find the total volume, we add all pieces together. In order to find the total volume, we add all these pieces together. So we're taking the sum. Taking the sum for I from 1 to n. Take the sum for I from 1 to n. When I is 1, we get the volume of the first piece. When I is 2, we get the volume of the second piece. And continue. When I is n, we get the volume of the last piece. Together, that's the volume of this shape. And the volume of this solid is very, very close to our actual solid. In order to find the actual solid, in order to find the actual volume, we must take a limit. Take a limit as the maximum delta si approach to 0. If the maximum delta si approach to 0, that means the largest piece will be very, very thick. If the largest piece is very, very small, then every rectangle here will be very, very small. The volume will be very, very close to the actual volume. So that's the actual volume of this solid. That's the actual volume of this solid as we take the maximum delta si approach to 0. That's the actual volume of this solid. And this is a Riemann sum. If you observe carefully, this is a Riemann sum. This is a Riemann sum. Then, by definition of integral, this can be written as integral from A to B. Integral from A to B. Pi times f of x squared. F of si star become f of x. Si star become x. Delta si become dx. That's the formula for the actual volume of this solid. We will notate r around the x-axis. In general, this formula can be written as integral of pi r squared. In general, this formula can be memorized as pi r squared. F of x represent, for each piece, f of x represent the radius of the little cylinder here. So we can memorize this as pi r squared. R is the radius. F of x represents the radius of each little cylinder here. So that's how we memorize this formula. Next, let's create an example. Let R be a region bounded by curves y equal to square root of x equal to 1, x equal to 4, and y equal to 0. Find the volume of the solid obtained by rotating R around the x-axis. So let's draw region R first. Y equal to square root of x looks like this. S equal to 1 is here. S equal to 4 is here. And y equal to 0 is the x-axis. So this is region R. We try to find the volume of the solid obtained by rotating R around the x-axis. When we rotate R around the x-axis, we have a solid looks like this. That's the region of the solid. That's the solid obtained by rotation. That's the solid obtained by rotation. Next, we try to find the volume of the solid. And the formula is integral of pi r squared. R is the radius. So we pick a little piece here. Pick a little piece. Draw a little piece perpendicular to the x-axis. And rotate this piece around the x-axis. It's a little disc here. For this disc here, what's the radius? We know that radius is the distance from the center to the edge. For this disc here, the x-axis is the center. This curve is the edge. Radius is distance from the center to the edge. So the radius of the disc is distance from center to the edge. In order to find this distance, we use upper curve minus the lower curve. Upper curve is square root of x. Lower curve is y equal to 0. That's the radius of this disc. Distance from center to the edge. In order to find the distance, we use upper curve minus lower curve. Upper curve is square root of x. Lower curve is 0. So square root of x minus 0. That's the distance from the center to the edge, which is the radius of the disc. That's square root of x. So the radius is square root of x. Then plug in. The volume is the integral of pi r squared. Pi is a constant. R is square root of x. The variable here is x, so take dx. Here x varies from 1 to 4. Here x varies from 1 to 4. Then solve the integral. First of all, pi is a constant, I can pull it out. And square root of x squared is x. Next, we take antiderivative. We get s squared over 2, evaluate from 1 to 4. If I plug in 4, I get 16 over 2. If I plug in 1, I get 1 over 2. Together is 15 over 2. So the final answer is 15 over 2 pi. That's the volume of the solid. Next example. Find the volume of a cone whose base radius and height are 2 and 4 respectively, which means the base radius is 2 and the height is 4. How can we find the volume of the cone? We know that the volume of a cone is 1/3 pi r squared h. If we use this formula, its volume is 1/3 times pi times r. Here r is 2. Height is 4. If we calculate this, 2 squared is 4. 4 times 4 is 16. 1/3 times 16 is 16/3. If we use the formula from the cone, we get 16/3 pi. But how can we find the volume using calculus? In order to find the volume of a cone, we try to rotate a triangle. When we rotate a triangle, we can obtain a cone. When we rotate a triangle, we have a cone. We can obtain a cone. So let me draw the triangle first. Consider this triangle. We have distance 2 here and distance 4 here. If we rotate the triangle around the x-axis, we have a cone. The base radius is 2 and the height is 4. If we rotate the triangle around the x-axis, we have a cone whose base radius is 2 and the height is 4. Now, for this triangle here, we know that the lower curve is an x-axis, which is y equal to 0. How can we find upper curve here? The upper curve here is a straight line. Is a straight line. Equation for a straight line is always y equal to ms plus b, where b is the y-intercept, m is the slope. Here we can see that the y-intercept is 2, so b is 2. Here we can see that y-intercept is 2, so b is 2. How can we find the slope of this line? Slope is always rise over long. Here rise is 2, long is 4. Rise over long. Slope is always rise over long. Here rise is 2, long is 4. The line is going down. Slope is negative. Slope is negative. Slope is always rise over long. Here rise is 2, long is 4. 2 over 4 is half. Rise over long. 2 over 4 is half. The line is going downward from left to right, so slope is negative. Y-intercept is 2. A straight line is always in the form of y equal to ms plus b. Here the slope is negative half. B is 2. Y-intercept is 2. So that's the upper curve. That's the lower curve. This is region R. Next, in order to find the volume of this solid, we pick a little piece here. Take this piece as a sample. If we rotate this piece around the x-axis, it's a disk. If we rotate this piece around the x-axis, it's a disk. And the radius of the disk is the distance from the center to the edge. The radius of the disk is the distance from the center to the edge. X-axis is the center. The edge is the upper curve here, half of x minus 2. So for distance from the center to the edge, we use upper curve minus lower curve. Upper curve is negative half x plus 2 minus lower curve. Lower curve is y equal to 0. For distance, we use upper curve minus lower curve. And the radius is distance from center to the edge. We use upper curve minus lower curve. Half of x plus 2 minus 0. If we simplify, this can be rewritten as 2 minus half of x. That's a radius. And then use the formula. The volume of the rotated region is integral of pi r squared. R is 2 minus half of x squared dx. And then here, x varies from 0 to 4. For this triangle here, x varies from 0 to 4. So take integral from 0 to 4. Then simplify. Expand the perfect square first. 2 squared is 4. 2 times half of x is x. Times 2 is 2x. Then half of x squared is quarter of x squared dx. Here pi is a constant, I can put it outside. Then take antiderivative for each term individually. If I take antiderivative for 4, I get 4x. Take antiderivative for 2x, I get x squared. Take antiderivative for 1 over 4x squared, I get 1 over 4 times s cubed over 3. Evaluate from 0 to 4. If I plug in 4, 4 times 4 is 16. 4 squared is also 16. 4 cubed is 64. 64 divided by 4 is 16. If I plug in 0, I get 0, 0, 0. So together, 16 minus 16 can cancel. We get pi times 16 over 3, which is 16 over 3 pi. Let's match what we have here. So we get exactly the same answer. That's how we find volume. That's how we find volume of a cone using calculus. Next example. Let R be a region bounded by curves y equals square root of x, s equal to 1, s equal to 4, and y equal to 3. Find the volume of the solid obtained by rotating R around the x-axis. So let's draw region R first. R is a region bounded by curves y equal to square root of x, s equal to 1, s equal to 4, and y equal to 3. Let's draw each curve first. Y equal to square root of x looks like this. S equal to 1 looks like this. S equal to 4 looks like this. And y equal to 3 is a horizontal line. So that's the region bounded by all 4 curves. That's the region bounded by all 4 curves. This is region R. Next, rotate region R around x-axis. If we rotate region R around x-axis, what do we get? If we rotate region R around x-axis, I have a solid looks like this. But there's a hole inside. There's a hole inside. I have a solid with a hole inside. If I rotate region R around x-axis, I have a solid with a hole inside. In order to find the volume, we use the outer volume minus the inner volume. Here, in order to find the volume of an outer solid, we use the formula pi r squared, integral of pi r squared. And for the volume of the inner solid, we also use pi r squared. But this r and this r, they are not the same thing. In order to make a difference, use capital R to represent the outer radius. Use small r to represent the inner radius. The bound is the same. The bound is the same. So this integral can be rewritten as integral pi of capital R squared minus small r squared, where capital R represents the outer radius, small r represents the inner radius. Now, what does it mean? Outer radius, inner radius. Let's take a little piece here, origin R. Let's take a little piece. Take a little piece perpendicular to the x-axis. If we rotate this piece around the center, if we rotate this piece around the center, if we rotate this piece around the center, I have a disc here with a hole inside. Since there are two circles, the outer radius is the distance from the center to the further curve. This curve is further away from the center. This curve is closer to the center. This curve is further away from the center. Outer radius is this distance from center to the further curve. Center is equal to 0. Distance from 0 to 3, we use 3 minus 0. Radius is always positive. We use 3 minus 0. Radius is always positive, so we use 3 minus 0. That's the outer radius, which equal to 3. The inner radius is the distance from the center to the closer curve. Here, this curve is closer. Square root of x is closer. Distance from the center to square root of x is square root of x minus 0. We use upper curve minus lower curve. Distance is always positive. Use upper curve minus lower curve. Use square root of x minus 0, which is square root of x. That's the inner radius. That's the outer radius. That's the inner radius. Then apply the formula. Volume is the integral of pi capital R squared. Capital R is 3 minus small r squared. Small r is square root of x dx. Here, x varies from 1 to 4. Here, x varies from 1 to 4. And here, pi is a constant. I can put it outside. 3 squared is 9. Square root of x squared is x. Then take antiderivative. We get 9 over 2. We get 9x minus x squared over 2. Evaluate from 1 to 4. If we plug in 4, I get 36 minus 16 over 2. If I plug in 1, I get 9 minus 1 over 2. Together, 16 over 2 is 8. 36 take away 8 is 28. 9 minus half is 17 over 1. 17 over 2. Then 28 take away 17 over 2 is 39 over 2. Which is 39 over 2 times pi. That's the volume of this solid. Next example. Let R be a region bounded by curves y equal to s squared plus 4 and y equal to s plus 6. Part A. Find the volume of the solid bounded by rotating R around the line y equal to 2 Part B. From the volume of a solid obtained by rotating R around the line y equal to 10. So let's draw region R first. R is a region bounded by two curves, y equal to s squared plus 4. That's a parabola open upward. Y equal to s squared plus 4, and y equal to s plus 6. S plus 6. That's a straight line. Slope is 1. Y-intercept is 6. So the parabola is y equal to s squared plus 4. The straight line is y equal to s plus 6. That's region R. Part A. Rotate the volume of the solid obtained by rotating R around the line y equal to 2. Y equal to 2 is this line here. That's the center, y equal to 2. So rotate the region around the line y equal to 2. I have a solid looks like this. There's a hole inside. That's a solid with a hole inside. Now, if there's no hole inside, the formula is integral of pi r squared. This is called a disk method. If there's a hole inside, the formula is integral of pi capital R squared minus small r squared. This is called a washer method. Because this solid looks like a washer, there's a hole inside. This solid looks like a washer, there's a hole inside. Now, if there's a hole inside, we use washer method. Integral of pi r squared minus small r squared. Big R, capital R, is the outer radius. Small r is the inner radius. Now, what is the outer radius? What's the inner radius? Let's draw a little piece here. On region R, let's draw a little piece. Draw a piece perpendicular to the x-axis. Draw a piece perpendicular to the x-axis. Then, based on this piece, we can see that if we rotate this piece around the center, we have a disk with a hole inside. The outer radius is a distance from the center to the further curve. Here the further curve is a straight line, y equal to x plus 6. The center is 2. Distance from x plus 6 to 2, we use upper curve minus lower curve. Radius is always positive. Use upper curve minus lower curve. X plus 6 minus 2. Use upper curve minus lower curve. Use upper curve minus lower curve. The center is 2. Further radius is s plus 6. That's an upper curve. That's a lower curve. Use upper curve minus lower curve. Radius is always a distance from the center to the edge. Here we use upper curve minus lower curve. That's a radius. Take x plus 6 minus 2. That's x plus 4. For the inner radius, that's the distance from center to the closer curve. Distance from the center to the closer curve. Here the closer curve is a parabola. S squared plus 4. For the distance from s squared plus 4 to 2, we use upper curve minus lower curve. S squared plus 4 minus 2. That's s squared plus 2. So that's the further radius. That's the closer radius. Then apply the washer method. Volume is integral pi capital R squared s plus 4 square minus s squared plus 2 square dx. Now what's the bound here? The left bound is this point, right bound is that point here. In order to find the left bound and right bound, we set these two equations equal to each other, because that's the intersection of these two curves. We set these two equations equal to each other. Set s squared plus 4 equal to s plus 6. Then solve the equation for x. We have s squared minus x minus 2 equal to 0. If I factor, I get s minus 2 times s plus 1. Solve the equation, s is 2, s is negative 1. So the smaller number is negative 1. Larger number is 2. So lower bound is negative 1, upper bound is 2. Then solve the integral. Let's simplify what's inside the bracket first. X plus 4 squared can be written as s squared plus ax plus 16 minus s squared plus 2 squared can be written as x to the power 4 minus 4s squared minus 4 dx. Then here pi is a constant, I can put it outside. If I combine like terms, I get negative x to the power 4 minus 3x squared plus ax plus 12 dx. Then take antiderivative. That's negative 1. Take antiderivative. We get negative x over x to the power 5 over 5 minus s cubed plus 4s squared plus 12x. Evaluate from negative 1 to 2. If I plug in 2 for x, I get negative 32 over 5 minus a plus 16 plus 24. If I plug in negative 1 for x, I get 1 over 5 plus 1 plus 4 minus 12. Then simplify. Negative 32 over 5 minus 1 over 5. That's negative 33 over 5. Negative a plus 16 is a. A plus 24 is 32. 32 minus 1 is 31. 31 minus 4 is 27. 27 plus 12 is 39. That's pi times 162 over 5, which is 162 over 5 pi. That's part A. The volume of the solid obtained by rotating R around the line y equal to 2. Next, for part B, find the volume of the solid obtained by rotating R around the line y equal to 10. Y equal to 10 is somewhere here above both curves. Let me draw the picture over. For part B, R is the region between two curves. Y equal to s squared plus 4 and y equal to s plus 6. That's region R. For part B, notate this region around the line y equal to 10. Assume y equal to 10 is somewhere here. Assume that's the line y equal to 10. Notate this region around the region y equal to, around line y equal to 10. The solid looks like this. That's the solid. That's the solid. We will take R around the center. That's a solid. So here we can see that there's a hole inside. There's a hole inside. We need to use Washer method. For Washer method, the formula is integral of pi capital R squared minus small r squared. Here, capital R represents the further radius. Small r represents the closer radius. That's the outer radius, that's the inner radius. Now, let's draw a little piece around the center on region R. Draw a little piece perpendicular to the x-axis. If we rotate this piece around the center, the picture looks like a disc. And there's a hole inside. That's what we get when we rotate this piece around the center. Now, the outer radius is the distance from the center to the further curve. Now here, that's the center, y equal to 10. The further curve, now it's a parabola. The parabola is further away from the center. The straight line is closer to the center. So the parabola is now the outer radius. It's a further curve. For the outer radius, we find distance from the center to the further curve. For outer radius, we find distance from the center to the further curve. Here the center is 10. Further curve is s squared plus 4. To find the distance, we use upper curve minus lower curve. And this time, 10 is the upper curve. The parabola is the lower curve. 10 is the upper curve. The parabola is the lower curve. So the distance from center to the edge is the radius. We use upper curve minus lower curve. That can be rewritten as 6 minus s squared. That's an outer radius. For the inner radius, we try to find distance from the center to the closer curve. Here, the closer curve is the straight line. The center is 10. And the closer curve is y equal to s plus 6. Radius is distance from center to edge. So if one distance from y equal to 10 to y equal to s plus 6. For distance, always use upper curve minus lower curve, because radius is always positive. Use upper curve minus lower curve. Use 10 minus x plus 6. Then combine like terms, we get 4 minus x. That's the inner radius. That's the outer radius. That's the inner radius. Then plug into the formula. Volume is integral of pi capital R square minus small r square dx. And what's the boundary here? What's the upper bound and lower bound? The upper bound and lower bound are the intersections of these two curves. And from part A, we know that the intersection is 2 and -1. So that's -1, that's 2. That's the lower bound, that's the upper bound. Then solve the integral. First of all, pi is a constant, we can pull out pi first. Pi is a constant, we can pull out pi first. If we pull out pi, we can expand the perfect square here. That's 36 minus 12s squared plus x to the power 4 minus 16 plus ax minus s squared dx. Then combine like terms. Combine like terms, we get x to the power 4 minus 13s squared plus ax plus 20 dx. Next, take antiderivative. We get x to the power 5 over 5 minus 13s cubed over 3 plus 4s squared plus 20x. Evaluate from -1 to 2. If I plug in 2, I get 32 over 5. 2 cubed here is a. A times 13 is 104 over 3. 2 squared is 4. 4 times 4 is 16. 2 times 20 is 40. If I plug in -1, I have -1 over 5 plus 13 over 3 plus 4 plus 20. It should be -20 here. -1 times 20 is -20. Then adding up. 32 over 5 minus -1 over 5 is 33 over 5. -104 over 3 minus 13 over 3 is -117 over 3. 16 plus 40 is 56. 56 minus 4 is 52. 52 minus -20 is 72. Here, -117 over 3 is 39. -39 plus 72 is 33. over 5 minus 33 is 132 over 5, which is 132 over 5 pi. That's the volume of this solid. Next example. Let R be a region bounded by curves y equal to s squared and y equal to 4 in quadrant 1. Part A. Find the volume of the solid obtained by rotating R around the y-axis. Part B. Find the volume of the solid obtained by rotating R around the line x equal to 2. Part C. Find the volume of the solid obtained by rotating R around the line x equal to -2. So, let's draw region R first. R is the region bounded by curves y equal to x squared and y equal to 4. Y equal to x squared is a parabola open upward, passing through the origin. Y equal to 4 is a horizontal line. That's a region in quadrant 1. Then part A says, find the volume of the solid obtained by rotating R around the y-axis. This is the y-axis. We rotate the solid around the y-axis. If we rotate R around the y-axis, that's a solid. That's a solid. Now, be very, very careful. For this solid, we rotate R around a vertical line. In general, when we rotate a solid around a horizontal line, we take antiderivative with respect to x. When we rotate a solid around a vertical line, we take antiderivative with respect to y. We take integral here with respect to y. So here, if we rotate a region around a vertical line, we pick horizontal pieces. In general, when we rotate a region around a horizontal line, we pick vertical pieces. The pieces must always be perpendicular to the center. The sample piece we choose must always be perpendicular to the center. The chosen sample piece must always be perpendicular to the center. The chosen sample piece must always be perpendicular to the center. In every example, the chosen sample piece must always be perpendicular to the center. The chosen sample piece must always be perpendicular to the center. So same thing here, we choose a sample piece perpendicular to the center. Our center here is the y-axis. So choose a sample piece on region R perpendicular to the center. If we rotate this piece, we have a disk and there's no hole inside. If we rotate this piece around the center, we have a disk, there's no hole inside. If there's no hole inside, we apply the disk method. That's integral of pi r squared. That's disk method. If there's no hole inside, we apply disk method. Now, since we are taking antiderivative with respect to y, we must write x in terms of y. The parabola is y equal to x squared. If we write x in terms of y, in quadrant 1, x is positive. That's x equal to square root of y. The center here is x equal to 0. The y-axis is x equal to 0. What's the radius? What's the radius? Radius of the disk is the distance from the center to the edge. Here the edge is this curve, x equal to square root of y. Center is 0. In order to measure a horizontal distance, we use right side curve minus left side curve. In order to measure a horizontal distance, we use right side curve minus left side curve. Right side curve here is a parabola, x equal to square root of y. Left side curve is y-axis, which is x equal to 0. So for the radius, we use right side curve minus left side curve. Square root of y minus 0, which is square root of y. That's the radius. Then plug in. The volume is the integral pi r squared dy. Here, y varies from 0 to this line. This line is y equal to 4. So y varies from 0 to 4. For this region here, y varies from 0 to 4. Then solve the integral. We get pi times y dy. Take antiderivative with respect to y. I get pi times y squared over 2, evaluate from 0 to 4. If we plug in 4, we get 16 over 2, that's 8. If I plug in 0, I get 0. So the answer is a pi. So the volume of this solid is a pi. Part B. Find the volume of a solid obtained by rotating r around a line s equal to 2. S equal to 2 is here. So rotate this region around the line s equal to 2. Let me draw the picture over. For part B, the picture looks like this. That's a region in quadrant 1. That's a boundary region in quadrant 1. The center, in part B, the center is s equal to 2. In part B, that's the center s equal to 2. We rotate this region around the center s equal to 2. If I rotate this region around the center s equal to 2, it looks like this. And there's a hole inside. There's an empty region inside. The inside is empty here. There's empty region inside. If there's empty region inside, we must use Washer method. Washer method is, if there's a hole inside, we need to use Washer method. Washer method is integral of pi outer radius minus inner radius. If there's a hole inside, we need to apply Washer method. If there's no hole inside, we apply disk method. If there is a hole inside, apply the Washer method. Capital R represents outer radius. Small r represents inner radius. So what's an inner radius? Let's pick a little piece on region R first. Since the center is s equal to 2, that's a vertical line. Our sample piece must be a horizontal piece. In general, this piece, the sample piece, must be perpendicular to the center. The sample piece must always be perpendicular to the center. Then rotate this piece around the center. We can see that there's a hole inside. So the outer radius is the distance from the center to the further curve. The further curve is this line here. This line is the y-axis, which is s equal to 0. Outer radius is distance from the center to the further curve. The further curve here is the y-axis. Y-axis is the line s equal to 0. The center is s equal to 2. For the distance from the center to the outer radius, we use right side curve minus left side curve. Here, right side curve is 2. Right side curve is 0. We use 2 minus 0. Radius is always positive, so we need to use right side minus left side to make it positive, which is 2. Inner radius is distance from the center to the inner curve. The inner curve is a parabola here. Since we are doing dy, since we are taking antiderivative with respect to y, we write x in terms of y. So the parabola is s equal to square root of y. For the distance from center to the edge, we use right side curve minus left side curve. For horizontal distance, we use right side curve minus left side curve, which is 2 minus square root of y. That's the inner radius. Then plug in. The volume is integral of pi times outer radius minus inner radius. Take integral from 0 to 4. This line is y equal to 4. The origin is y equal to 0. This line is y equal to 4. So take integral from 0 to 4. Next, solve the integral. 2 squared is 4. Expand the perfect square, we get 4 minus plus 4 square root of y minus y dy. Then simplify, combine like terms. I can first of all pull out pi. 4 can cancel. I get 4y to a half minus y dy. Then take antiderivative. We get 4y to the 3 over 2 over 3 over 2 minus y squared over 2. Evaluate from 0 to 4. Next, simplify. 4y to the 3 over 2 divided by 3 over 2 can be rewrite as 4 times 2 over 3 y to the power of 3 over 2 minus y squared over 2. Evaluate from 0 to 4. If I plug in 4 for y, 4 to the power of 3 over 2 is a. I get a over 3 times a minus 4 squared is 16. 16 over 2 is a. If I plug in 0, I get 0. Then multiply. A times a is 64. 64 over 3 minus a. A can be written as 24 over 3. That's 40 over 3. So the final answer is 40 over 3 pi. That's the volume of this solid. That's part B. Part C. Find the volume of the solid obtained by rotating R around the line s equal to -2. S equal to -2 is somewhere here. Rotate R around this line. S equal to -2. Let me draw the picture over. Region R looks like this. That's a region. Rotate the region around the line. S equal to -2. S equal to -2 is a vertical line passing through -2 on the x-axis. That's the line S equal to -2. Rotate this region around the line S equal to -2. The solid looks like this. And we can see that there's a hole inside. There's a hole inside. If there's a hole inside, we must use washer method. If there's no hole, use disk method. When there's a hole inside, use washer method. Washer method is integral of pi outer radius square minus inner radius square. And since the center is a vertical line, we take antiderivative with respect to y. Since the center is a vertical line, we take antiderivative with respect to y. Now, in order to decide the outer radius and the inner radius, we choose a sample piece on the region here. The sample piece must always be perpendicular to the center. The sample piece must always be perpendicular to the center. If you rotate this piece around the center, we have a disk with a hole inside. That's the center. Outer radius is the distance from the center to the further curve. Here the further curve is y equal to s squared. If I write x in terms of y, that's the same as s equal to square root of y. Outer radius is always distance from the center to the further curve. Here the further curve is a parabola. In order to find the distance, we use right side curve minus left side curve. In order to find the distance, we use right side curve minus left side curve, which is square root of y minus -2. That's square root of y plus 2. That's the further radius. For the closer radius, that's the outer radius. For the inner radius, we find the distance from the center to the closer curve. The closer curve is this line. This line is the y-axis. Y-axis is s equal to 0. This line is the y-axis. Y-axis is always s equal to 0. So, for the inner radius, that's the distance from the center to the closer curve. For distance, we use right side curve minus left side curve. For horizontal distance, always use right side curve minus left side curve. So that's right side, that's left side. We get 0 minus -2. Double negative is positive. We get 2. So the inner radius is 2. That's an outer radius, that's the inner radius. Then plotting the formula. Volume is the integral of pi outer radius square minus inner radius square. Outer radius is square root of y plus 2 square. Inner radius is 2 square dy. Here y varies from 0 to 4. Origin is 0. This line is y equal to 4. Then simplify and take antiderivative. I can first of all pull out pi. Pi is a constant. If I expand the perfect square, I get y plus 4 square root of y plus 4 minus 4 dy. Then combine like terms. Combine like terms. 4 get cancelled. I get y plus 4y to a half. Then take antiderivative. I get y squared over 2 plus 4 times y to the 3 over 2 over 3 over 2. Evaluate from 0 to 4. Simplify first. I get y squared over 2 plus 4 times 2 over 3 times y to the power of 3 over 2. Evaluate from 0 to 4. If I plug in 4, 4 squared is 16. 16 over 2 is 8. If I plug in 4 here, 4 to the power of 3 over 2 is 8. 4 times 3 over 2 is 8 over 3. If I plug in 0, I get 0. Here I get a plus 64 over 3. A can be written as 24 over 3. 24 plus 64 is 88. I get pi times 88 over 3, which is 88 over 3 pi. That's the volume of this solid.